Have you ever stopped to think how something can be in two places at once, or how two particles can stay linked even when separated by light years? Tonight, we're exploring the quiet strangeness beneath reality, the world that makes everything possible. Welcome to The Whispering Scientist. This channel is all about calm curiosity, where you can learn something new about the universe without rushing through it.
I'd love to know where you're watching from and what time it is where you are.
It's always fascinating to see how far these quiet journeys reach. If you enjoy peaceful explorations of science, please give the video a like and consider subscribing. It really helps. And to those already subscribed, thank you. You're the reason this little corner of calm keeps growing. Don't forget to tap the notification bell so you won't miss the next slow drift through science and space. Hopefully, this video isn't too interesting to keep you awake. But if it is, at least you'll fall asleep knowing a little more about the most mysterious part of physics. Quantum physics began, not with a grand theory of everything, but with a simple problem that refused to go away. For centuries, the nature of light and heat had been studied, but the deeper scientists looked, the more the old, comforting rules of nature started to fall apart. Light sometimes acted like a smooth, continuous wave, yet other times behaved like tiny, discrete particles.
Matter, once thought to be solid and predictable, turned out to shimmer with probability and uncertainty.
Out of that confusion came a new revolutionary idea that everything is ultimately built on discrete steps and fundamental limits. The word quantum comes from the Latin for how much. It describes something that is counted, not continuous, suggesting a world built from steps instead of slopes. In the late 1800s, scientists believed that energy flowed smoothly, much like water pouring in an unbroken stream from a jug. But something strange began to happen in experiments involving light and heat. Energy stubbornly refused to behave continuously. It arrived in small, exact amounts, as if nature were paying in small coins instead of banknotes. This precise moment at the turn of the century was the quiet, almost accidental birth of quantum physics. It was the discovery that reality itself seems to fundamentally count. This profound idea first appeared through the work of a German physicist named Max Planck. In the year 1900, Planck was attempting to explain a seemingly straightforward phenomenon: the light given off by hot objects, such as a piece of iron glowing in a forge. Classical physics, the established set of rules governing the world, made an impossible prediction regarding this light. When applied to the blue and ultraviolet parts of the spectrum, classical physics predicted an infinite brightness, a colossal energy output that clearly didn't happen in reality. This theoretical disaster was famously known as the ultraviolet catastrophe. Planck's solution was daring, even radical for its time. He suggested that energy could only be emitted or absorbed in specific tiny packets, which he called quanta. He did not initially believe this idea represented a fundamental truth about the universe. He thought of it as a mere mathematical trick to make his equations align with the observed data. Yet, that mathematical trick laid the cornerstone for all of modern physics. The size of each of these energy packets depended on the light's frequency and a brand new constant of nature, now universally known as Planck's constant, symbolized as $8. This tiny number, roughly $6.6 times 10 or $34 joule seconds, defines the grain of the universe. It sets the smallest possible increment, the minimum scale at which energy can be exchanged. It is unimaginably small, yet it sets the rhythm for everything that happens at the atomic and subatomic scales. Because Planck's constant is not zero, the universe hums with discreteness. Energy levels in atoms come in fixed steps, not continuous slopes, forcing electrons to jump between them rather than sliding gradually. This jumpiness is what produces the sharp, precise colors in neon lights and the distinct lines found in atomic spectra, the unique fingerprints of the elements. Without Planck's constant, energy would flow continuously, atoms would collapse. There would be no distinct chemistry as we know it, and the very structure of solid matter would vanish at the level defined by Planck's constant. The world begins to blur. Particles are no longer tiny, solid billiard balls bouncing predictably along neat paths. Instead, they behave like waves of possibility, spread out over space, overlapping and interfering like ripples on water. When you imagine an electron inside an atom, it is not whirling in a perfect orbit like a miniature planet. It exists as a cloud of probability, a fuzzy region where it is most likely to be found. This was a staggering shift. For centuries, certainty was the goal of science: precise laws, definite locations, and predictable outcomes. Quantum physics replaced that comfort with probability. It cannot tell you exactly where a single particle will land, only the odds of finding it in each possible place. This randomness is not chaotic. It is a statistical harmony that makes lasers coherent, transistors function, and the stars themselves shine with consistent, predictable light. At its heart, quantum physics tells us something profound. The universe isn't a fixed machine grinding forward in perfect order. It's a set of probabilities waiting to unfold. Energy comes in steps, outcomes arrive by chance, and certainty is a luxury that only exists at human scales. Beneath the everyday world lies a quiet sea of numbers and waves, an ocean where every event begins as a question, not an answer. Planck could not have known how far his simple formula would reach. What began as an attempt to solve a color problem in glowing metal became the foundation for all of modern physics, marking the border between the classical and the quantum, between the smooth and the stepped, between the predictable and the strange. From these tiny, discrete beginnings, the entire, magnificent structure of the universe emerges not as a solid block of certainty, but as a shimmering pattern of possibilities. The quiet revolution sparked by Max Planck's constant, the tiny measure of reality's graininess, led directly to a profound shift in how we understand matter itself. At the level set by this constant, the old certainties of the world begin to dissolve. Particles are no longer tiny billiard balls bouncing predictably along neat, predetermined paths.
Instead, they behave like waves of possibility,
Spread out over space, overlapping and interfering with one another like ripples on a still, silent pond. When you imagine an electron, the fundamental constituent of all atoms, it's essential to abandon the comforting image of a miniature planet orbiting a nucleus. That classical picture is fundamentally misleading. Rather than whirling in a perfect, solid orbit, the electron exists as a cloud of probability, a fuzzy, three-dimensional region where it is most likely to be found. The boundary between a localized, definite particle and a spread-out wave of energy becomes less like a strict rule and more like a fluid state, a transient mood of nature itself. This realization represented a staggering philosophical shift for science. For centuries, the entire endeavor had been focused on finding absolute certainty, precise laws, definite locations, and perfectly predictable outcomes. Quantum physics replaced that comfortable determinism with probability. It is a framework that cannot tell you precisely where a particle will land at a given moment, but it can tell you the exact odds of finding it in each possible place. This might sound initially like a step backward, an admission of ignorance, but it is actually a far more powerful and accurate way of describing nature's deepest architecture. Where classical physics fails at the extremes, inside atoms, at subatomic distances, or near the speed of light, quantum physics shines with uncanny, unmatched accuracy. Even the simple concept of an event or a particle's journey changes meaning at these minuscule scales. A photon, a packet of light energy, doesn't travel like a marble rolling across a table, following one single, fixed path. Instead, it travels like a story being told many ways at once. Every conceivable route from its starting point, point A, to its ending point, point B, quietly contributes to the final outcome. Each possible path acts as a tiny, invisible wave that can either reinforce or cancel out the waves associated with other paths. The result of this simultaneous exploration of possibilities is a delicate interference pattern, which acts as a permanent record of all the possibilities that could have happened but ultimately didn't. This is why the quantum world often feels both ghostly and incredibly precise at the same time. The particles are exploring an infinite landscape of potential, yet they converge statistically onto patterns dictated by this internal wave-like interference. Planck's constant, that minuscule number we discussed, is the silent metric that sets the stage for this dual behavior. It is the measure of how grainy reality is, the smallest possible tick on nature's cosmic clock. If this constant were somehow equal to zero, everything would behave purely classically. Energy would flow smoothly, motion would be continuous, and certainty would universally reign. But because Planck's constant is a non-zero fundamental value, the universe hums with discreteness. The necessity of energy coming in discrete steps rather than flowing continuously explains why the energy levels in atoms are like rungs on a ladder rather than a continuous ramp. Electrons must jump between these rungs, absorbing or emitting exact quanta of energy rather than sliding gradually. This jumpiness is not a glitch. It is the fundamental mechanism that generates the sharp, clear colors we see in neon lights and the precise spectral lines that act as the chemical fingerprints of every element in the universe. Without Planck's constant enforcing this quantum rule, there would be no distinct atomic structure, no chemistry to drive life, and no solid, stable matter at all. When quantum theory first emerged in the 1920s, the idea that energy and matter could exist in such probabilistic and discrete ways was met with skepticism and resistance from many established physicists. It seemed almost mystical, defying all common-sense intuition established over centuries. Yet experiment after experiment confirmed its strange accuracy. Light behaved as both a wave and a stream of particles. Electrons interfered with themselves, behaving as if they were spread out, yet always struck detectors one at a time, localizing instantly. The mathematics of quantum mechanics, developed by brilliant minds like Erwin Schrödinger, Werner Heisenberg, and Paul Dirac, proved not only successful but absolutely indispensable. This framework successfully predicted the detailed behavior of atoms, explained the intricate structure of the periodic table of elements, and laid the precise, necessary foundation for virtually every modern technology that shapes our world today. It is easy for us to think of probability as a sign of mere ignorance, as if the universe knows the definitive answer and we simply lack the tools to see it. However, quantum probability is deeper than that. It is fundamentally built into the nature of things. Reality doesn't possess a single, fixed, hidden outcome that is merely waiting to be revealed. Rather, reality genuinely exists in a spread of potential states until the moment it is compelled to choose. Even then, it seems to choose randomly, yet always according to a set of profound, exact mathematical rules that never miss. This randomness is not chaotic. It is a higher form of statistical harmony, the very consistency that allows technologies like transistors and lasers to work, and that dictates the stable fusion process within the stars themselves. Planck could not have possibly known how far-reaching his simple formula would be. What began as a humble attempt to fix an impossible color problem in glowing metal became the irreversible foundation for all of modern physics, defining the very limits of reality itself. His tiny constant, $2, is now woven into the core equations that describe everything from semiconductor technology to the behavior of black holes. It stands as the permanent border between the classical world, which appears smooth and predictable, and the quantum world, which is stepped, probabilistic, and fundamentally strange. At its core, the electron's wave-like nature is a promise, a shimmering possibility that reality is far more flexible and creative than our limited, large-scale intuition would ever allow. Beneath the comforting precision of our everyday world lies an underlying sea of possibility where every entity holds the potential to be many things at once. Light has always been a shapeshifter, a fundamental mystery that resisted simple definition. Sometimes it behaves like a gentle wave, spreading out and interfering with itself, curling around obstacles and bending smoothly through glass. At other times, it arrives in sudden, sharp sparks, tiny, countable bursts of energy called photons, each one delivering a single, precise punch of light. For centuries, scientists argued over which version was the ultimate reality. Was light a continuous vibration, spreading like a ripple in a pond, or was it a shower of minute particles traveling like tiny arrows? The answer, as quantum physics revealed, is beautifully and fundamentally inconvenient. Light is both. And yet, depending on how you look at it, it is neither. The story of this dual nature is long, beginning well before quantum theory existed. In the 17th century, the celebrated physicist Isaac Newton believed light was made of minute, solid particles he called corpuscles. Around the same time, the Dutch astronomer Christian Huygens imagined light as a wave, a continuous vibration spreading through an invisible medium. Both men were, in their own way, partly right and partly wrong. The argument seemed to be settled, at least temporarily, in the early 19th century through the ingenious experiments of Thomas Young. When Young passed light through two thin, parallel slits, it created a distinct pattern of bright and dark bands on a screen behind them. This was the unmistakable signature of interference. The light from one slit was combining with the light from the other, adding together to create the bright bands, and cancelling each other out to form the dark gaps, all in perfect, rhythmic order. It was elegant, undeniable, and entirely characteristic of waves overlapping. For nearly a century after Young's success, light was confidently defined as a wave. But then came something far stranger, a crack in the certainty of the wave model. In 1905, Albert Einstein, building on the groundwork of Planck, provided an explanation for the photoelectric effect, the phenomenon where shining light on a metal could eject electrons from its surface. Classical wave theory predicted that brighter light, carrying more total energy, should always release more electrons, regardless of its color or frequency. Yet, experiments showed clearly that color mattered above all else. Only light above a certain specific frequency, such as blue or ultraviolet, could knock electrons free. An intense, bright red light beam, even carrying vast amounts of total energy, could not dislodge a single electron. Einstein proposed that light's energy is not spread continuously, but comes in discrete packets, or quanta, later named photons. These photons behave like particles. A dim blue photon carried more energy than a red one, and therefore only the blue photon had enough energy to deliver a single, effective punch to eject the electron. From that moment, light's dual nature became absolutely impossible to ignore. When we measure it one way, we find waves, smooth, continuous, and spread out across space. When we measure it another way, we find particles, countable, localized, and discrete packets of energy. It's as if light waits to decide what definitive
form it wants to take until someone actively checks its
state. The famous double-slit experiment illustrates this beautiful duality more clearly than almost anything else in science. When light, or even single photons, pass through two slits and we do not observe which slit they go through, the characteristic interference pattern, the signature of waves overlapping, emerges. But if we set up detectors to watch and determine which slit each photon travels through, the interference pattern immediately disappears. Instead of soft fringes, we get two solid bars, exactly like what would be created by tiny bullets striking a wall. The mere act of observation changes the outcome. When the experiment is performed with single photons, it becomes truly mysterious. Each photon seems to go through both slits at once, interfering with itself, yet when it finally lands on the screen, it makes a single, localized dot, as if it were a particle choosing one precise path. Over time, those single dots slowly build up the complex interference pattern that only waves should produce. One photon at a time, nature paints a breathtaking picture of duality. And the boundary between energy and matter blurs further, for electrons too reveal this strange behavior. They are undeniably matter with a measurable mass and electrical charge. Yet, when scientists fire a stream of electrons through the very same double slits, they create identical, soft interference patterns. Each electron behaves like a spread-out wave, exploring multiple potential paths before being detected as a single, fixed point. The line between energy and matter dissolves. The wave nature of matter was formally predicted by Louis de Broglie in 1924, who proposed that every particle, from electrons to baseballs, has an associated wavelength determined by its momentum. The smaller and faster the particle, the shorter its wavelength. While your personal wavelength is far too minuscule to ever notice, the principle holds true for everything. So what exactly is waving? It is not a physical substance like water or air, but a probability field, a mathematical wave describing the chances of finding a particle in each place. This wave doesn't carry energy like a ripple on a pond. It carries crucial information about possibilities. Before a measurement, an electron exists in many potential locations at once, its probability weighted by the amplitude of its wave. After measurement, one single location becomes real, and the rest vanish like unchosen paths in a story. The more physicists studied this behavior, the more they realized that insisting on a single picture, either wave or particle, was missing the point. Reality at the quantum level isn't one thing or the other. It's something deeper that only appears as one or the other when it is observed or forced to interact. The wave-particle duality isn't a flaw in our understanding. It's a reminder that our rigid categories were built for larger, simpler things. We expect objects to be in one place, moving along one path and behaving predictably. The quantum world doesn't obey those expectations.
It dances between them.
Waves become particles, particles become waves, and the distinction is one of perspective, not of nature. The realization that light, which we had long considered a wave, could also behave like a particle immediately raised a fascinating and profound question. If light can be a particle, can a particle, true matter, also be a wave? This question pushed the boundary of quantum logic and led to the startling concept of matter waves, which profoundly redefines the nature of everything we perceive as solid. The line between energy and matter, already blurred by the discovery of the photon, began to dissolve entirely. A quiet French physicist named Louis de Broglie in 1924 formally predicted this wave nature of matter. He put forth a bold hypothesis: if light, which is wave-like, possesses a particle nature, then matter, which is particle-like, must also possess a wave nature. De Broglie proposed that every particle, from the smallest electron to the largest baseball, has an associated wavelength, now known as the de Broglie wavelength. This wavelength is determined by the particle's momentum. The rule is simple and elegant. The smaller and faster the particle, the shorter its associated wavelength. For large, macroscopic objects like a baseball or a human being, the wavelength is impossibly small, far too minuscule to ever be detected or measured. This is why our everyday world appears perfectly solid and fixed. The wave nature is there, but it is effectively irrelevant at our scale. However, for subatomic particles like electrons, the wavelength is large enough to influence their behavior dramatically. This wave-like behavior means that electrons are not just tiny marbles. They are ripples in a quantum sea, capable of interfering and diffracting just like light. This bold idea was confirmed only a few years later in 1927. Through experiments where scientists observed diffraction patterns from beams of electrons bouncing off crystals, these patterns were identical to those produced by X-rays, which are light waves. It was an unmistakable sign matter was officially wave-like too. The electron, the tiny constituent of all atoms, was a shapeshifter, existing as a particle that possessed the physical characteristics of a wave. The deep mystery is illustrated by the double-slit experiment when performed with single electrons. Each electron fired at the slit seems to go through both slits at once, exploring multiple potential paths simultaneously. As they travel, the wave associated with the particle interferes with itself, creating that characteristic pattern of bright and dark bands on the detector screen. Yet, when it finally arrives at the screen, it registers as a single, localized dot, as if it had chosen one definitive path in the final instant. Over time, as thousands of these single dots accumulate, they slowly build the smooth interference pattern that only waves should create. One electron at a time, matter paints a picture of duality and self-interference. So, if electrons and other particles are waves, what exactly is waving? It is not a physical medium like water, and it is not a stream of invisible material. It is a probability field, or a mathematical wave, the wave function, that describes the chances of finding the particle in each specific place. This wave doesn't carry energy in the way a ripple on a pond does. It carries crucial information about possibilities. Before a definitive measurement is made, an electron truly exists in many potential locations at once, its probability weighted by the amplitude of its wave. The wave function is a complex mathematical object that describes the full,
rich spread of all possibilities for the particle.
When this wave function is squared, the result yields the probabilities, the precise odds of finding the particle in one state versus another. This squared probability acts as the bridge, the translation mechanism, between the unseen quantum realm of overlapping waves and the measurable classical reality of a single, fixed observation. When a measurement occurs, we are not simply revealing a hidden truth that was secretly waiting to be discovered. Instead, the act of measurement forces the universe to select a single outcome from that landscape of possibility. One location becomes real and the rest vanish like unchosen narratives in a branching story. The more physicists studied this behavior, the more they realized that insisting on a single, fixed picture, either particle or wave, was missing the profound point. Reality at the quantum level isn't one thing or the other. It's a deeper, more unified entity that only manifests as one or the other when actively observed or forced to interact with the larger environment. The mathematics of the wave function holds both views without contradiction. This duality challenges our common-sense intuition, which is trained by the deterministic, large-scale world. But this very ambiguity is what makes quantum theory so robust and powerful. It explains why electrons settle into stable shells around an atom's nucleus rather than collapsing directly into it, why lasers emit pure, intense beams of light, and why certain materials can carry electrical current with zero resistance. The wave-particle duality isn't an embarrassing flaw in our understanding. It's a fundamental statement that our categories, built for large, simple objects, are too rigid for the subtle grammar of the quantum world. The universe doesn't limit itself to our definitions. It uses both sides of its nature whenever the context demands it. When a vast number of photons move together, their wave nature dominates, forming smooth beams of light. When you detect them one by one, their individuality shines through. The ability of matter to behave as a wave, to be a self-interfering particle, is the quiet, essential core of everything that follows in quantum mechanics. It's a deep truth that the universe is more flexible than our language, more creative than our traditional categories, and infinitely stranger than our basic instincts. What began as a contradiction became a deeper, unifying truth that everything in the universe is both a wave of possibilities and a single, solid fact, depending on when, where, and how we decide to look. The act of looking, in essence, is not passive. It is a profound and active form of participation in the unfolding of reality. Superposition is one of the most mind-bending ideas in all of physics, and it follows directly from the wave nature of matter we've explored. It tells us that at the quantum level, things don't simply exist in one state or another. They can, and often do exist, in many states at once. A single atom can be spinning clockwise and counterclockwise at the same time. A particle can take every possible path from one point to another simultaneously. Even the simple fundamental question, where is it, becomes slippery, because the definitive answer isn't one location, but a complex, overlapping range of possibilities that all genuinely coexist until something, usually a measurement or an interaction, forces the universe to decide and select a single outcome. To understand this, imagine flipping a coin. In the classical, everyday world, while it's spinning in the air, it is technically either heads or tails, even though we don't know which yet. The answer is fixed, hidden only by our ignorance. But in the quantum world, before the coin lands, it is not hiding a secret answer. It is genuinely both heads and tails at once, a delicate combination of probabilities superimposed upon each other. Only when it is observed, when the system interacts with its surroundings, does this superposition settle into a single, fixed outcome. This is the profound essence of quantum superposition, a temporary, fragile balance between all that could be and all that. Ultimately will be Erwin Schrödinger famously illustrated this idea in 1935 with his thought experiment involving a cat that is both alive and dead simultaneously. His intention was not to suggest that such a state is physically possible for a macroscopic object like a cat. Rather, he wanted to show just how absurd the rules of the quantum world can seem when scaled up to human size. Inside his imaginary box, the cat's fate depends on a single quantum event, such as the unpredictable decay of a radioactive atom. Before anyone looks, the atom exists in a superposition of both having decayed and not having decayed. Therefore, the cat, linked to the atom, is theoretically both alive and dead in a combined state. Only when the box is opened and the system is observed does the wave function collapse, selecting one outcome over the other. Schrödinger's cat remains a powerful, quiet reminder of how quantum possibilities fade rapidly into classical reality the moment they are observed or disturbed. This profound concept, that reality exists in a cloud of overlapping possibilities, may sound abstract, but it is the indispensable foundation of modern, cutting-edge technology. Every quantum computer, for example, is built entirely upon the principle of superposition. A classical bit, the fundamental unit of information in your phone or laptop, can be either 0 or 1. But a quantum bit, or qubit, can be both 0 and 1 at once, held in superposition. This capability allows quantum computers to process vast numbers of possibilities simultaneously, exploring a landscape of solutions in parallel. It is like trying every single combination of a complex lock at the exact same time, instead of the slow, painstaking process of trying them one by one. Superposition is not just about existing in two states. It is about how those states combine and interfere with one another. Every state in superposition carries a phase, a kind of hidden rhythm or timing that determines how it will interact with other states. When waves overlap, their phases can add together constructively to create bright spots, or they can cancel each other out destructively to create darkness. Quantum systems behave exactly the same way. The probabilities of different outcomes interfere with one another, amplifying some possibilities while gently erasing others. This is precisely what gives rise to the elegant interference patterns in experiments like the double slit, where even single particles seem to know about potential paths they didn't take. These patterns are the unmistakable fingerprints of superposition, showing that nature doesn't commit to a single path until it is absolutely forced to. The bright fringes, where the waves align, and the dark gaps, where they cancel, are not random. They are precise mathematical records of how possibilities interacted before one single outcome became real. Superposition might sound mystical, but it is remarkably logical once you accept the premise that the universe is fundamentally built on waves of probability. A particle's wave function contains the full spectrum of all its possible states, each weighted with a different amplitude and phase. When we perform a measurement, we are not uncovering a pre-existing truth. We are actively creating a truth, selecting one single outcome from that rich landscape of possibilities according to its probability. One of the most striking demonstrations of the scale of superposition comes from experiments with surprisingly large molecules. Scientists have managed to send entire clusters of atoms, sometimes hundreds or even thousands of atoms large, through double slits and still observe unmistakable interference patterns emerge. This means even these relatively complex systems can exist in overlapping states, like a single, unified object walking down two corridors at once. The larger the object, the more challenging it is to preserve this quantum behavior, because interactions with the environment tend to destroy superpositions, a process called decoherence. But the fundamental principle holds. Everything, from photons to fermions, has a quantum nature waiting just beneath its surface. It is tempting to think of superposition as mere indecision, as if particles are simply unsure of what to do. But this interpretation misses the point. The system is not confused, it is complete. It holds every possibility, each carefully weighted and mathematically balanced, until something disturbs it. In this sense, superposition is not a flaw or a glitch. It is how the universe keeps its creative options open. Every atom, every photon, every quantum system quietly carries within it a chorus of potential realities, all humming in synchrony until the music stops, and one singular note is chosen. Superposition also reveals that observation is a profoundly active process, never passive. When you measure something, you don't merely read its state, you help to fundamentally define it. This doesn't mean human consciousness magically alters reality. Rather, the key is the act of interaction, the physical exchange of information or energy that forces a quantum system to couple with its environment and lose its delicate coherence. The moment that crucial interaction happens, whether the observer is a scientist, a camera, or a tiny dust particle floating nearby, the delicate balance of superposition collapses, and the world resolves into a single, definitive story. Without superposition, the world would lose its shimmer. Lasers wouldn't amplify light so perfectly, atoms wouldn't form the stable chemical bonds necessary for life, and the colors of matter would fade into a dull monotony. The reason electrons remain suspended in their specific shells around a nucleus, rather than crashing into it, is because they exist in standing wave superpositions, stable patterns of probability that keep them suspended in perfect, non-collapsing harmony. When viewed through this lens, superposition is not a curiosity. It is the hidden, efficient grammar of the universe, the principle that allows reality to be flexible, adaptable, and surprisingly efficient, creating a world where certainty is merely a momentary surface phenomenon built on a deep, shimmering sea of overlapping possibilities. The concept of superposition, where a particle inhabits multiple states simultaneously, introduces the need to understand how these possibilities interact with one another. This interaction is governed by interference, a process that reveals the subtle, wave-like architecture underlying all reality and provides a direct path to understanding why the quantum world looks so utterly different from our stable, everyday experience. Every state in a superposition, as we discussed, possesses a phase, a kind of invisible internal timing or rhythm. This phase dictates the system's potential, determining how one possibility will reinforce or cancel another. When these quantum phases are perfectly aligned, when the rhythms match, they interfere constructively, amplifying the probability of a certain outcome. This amplification is what creates the bright fringes in the double-slit experiment. Conversely, when the phases are precisely misaligned, they interfere destructively, effectively erasing the probability of that outcome. This cancellation creates the dark gaps or nodes in the interference pattern. These patterns are not accidents. They are the precise mathematical fingerprints of superposition, records of how possibilities interact before one is ultimately chosen. The mathematics of quantum mechanics meticulously predicts the exact location and intensity of these fringes, demonstrating that the particles are indeed exploring all possible routes simultaneously, but they are doing so under the strict, elegant rules of interference. This phenomenon is what allows the quantum world to be both seemingly chaotic and astonishingly precise. The randomness is constrained by the statistical harmony of interfering probability waves. However, this profound quantum harmony is incredibly fragile. The ability of a system to maintain its overlapping phase-locked state is called coherence, and it is constantly under attack by the larger, messy world around it. The slightest disturbance, a collision with a stray air molecule, a flicker of light, or a tiny vibration can cause those delicate phases to drift out of sync, leading to the irreversible loss of quantum order. A process known as decoherence. Decoherence is the quiet, ceaseless mechanism that truly separates the quantum realm from the classical world we inhabit. It is not an abrupt, mysterious collapse of the wave function. Rather, it is a rapid process of information leakage. Every time a quantum system interacts with its environment, it becomes entangled or linked with the vast network of surrounding particles, spreading its fragile quantum information outward. Once that information is dispersed and entangled with the countless thermal and random fluctuations of the environment, it is practically impossible to recover or observe the original coherent state. To us, the macroscopic observer, the system appears to have instantaneously collapsed into a single, fixed outcome, losing its superposition. This explains why large objects like tables or even Schrödinger's cat appear to exist in only one state at a time. It's not that they stop being quantum, it is that their interactions with the hot, noisy world are so frequent and overwhelming that quantum coherence disappears in a time frame far too brief for us to perceive, often in less than a trillionth of a second. A baseball is still technically a quantum object with an associated wave function, but its constant, violent collisions with air, heat, and photons ensure that its wave function is immediately decohered, forcing it into a single, predictable location. Decoherence is the bridge that seamlessly connects the strange, probabilistic quantum realm to our stable, familiar, classical reality. It shows that the boundary between the two worlds is not marked by size but by isolation. The more effectively a system can be shielded from environmental noise, the longer it remains coherent, and the longer it exhibits its bizarre quantum properties. In modern technology, coherence is a precious commodity. The quest to build functional quantum computers, devices designed to harness superposition and entanglement, is fundamentally a race against decoherence. Quantum bits, or qubits, must maintain their delicate phase synchrony for long enough to complete complex calculations. Engineers employ extreme measures, cooling the circuits to temperatures just a hair above absolute zero, isolating them from all electromagnetic vibrations, and working within ultra-high vacuums, all to extend that fragile coherence time, often only by a few precious microseconds. Without constant vigilance against decoherence, the qubit loses its superposition and reverts to an ordinary, classical bit, collapsing the computation prematurely. Furthermore, the scale of coherence dictates the visibility of quantum effects. In atomic physics, coherence allows electrons to maintain their stable standing wave patterns around the nucleus, preventing the atom from collapsing. In condensed matter physics, coherence allows vast numbers of electrons in a superconductor to form Cooper pairs, gliding through the material in perfect synchrony with zero resistance. And in light, perfect coherence is the core principle behind the laser, where trillions of photons are coaxed into marching in lockstep, their waves perfectly synchronized, resulting in a narrow, intense beam that can travel for miles without spreading. The transition from a perfectly coherent state to a fully decohered state is not a flaw in the universe. It is a fundamental feature that enables stability. Without decoherence, the world would remain a permanent, chaotic blur of possibilities, never settling into the stable patterns we call reality. Without coherence, quantum phenomena like the formation of stable chemical bonds or the efficient movement of energy in photosynthesis could
never emerge. The interplay between interference and decoherence
defines the very architecture of potential. It shows that the universe is constantly keeping its options open through superposition and interference, while simultaneously forcing those options into the single, visible reality we know through the pervasive, unavoidable process of decoherence. The entire macroscopic world is, therefore, a vast, complex arrangement of decohered quantum particles, perpetually stabilized by the same laws that govern the deepest subatomic chaos, a harmonious balance achieved through a ceaseless, silent struggle against noise. The quantum world is full of surprises, but perhaps none is more fundamental or more misunderstood than uncertainty. In everyday life, uncertainty feels like ignorance. If you don't know where your keys are, it is not because their position is unknowable. It is simply because you haven't looked hard enough or haven't checked the right pocket. But in quantum mechanics, uncertainty is not a matter of poor eyesight or bad equipment. It is woven into the very fabric of reality.
Nature does not simply hide information from us.
In some profound cases, that information literally does not exist until we look for it. Werner Heisenberg first clearly stated this deep principle in the year 1927, and it is now known universally as the Heisenberg uncertainty principle. It states that for certain pairs of properties, such as a particle's position and its momentum, a measure of its mass and velocity, you can never know both with perfect simultaneous precision. The tighter you pin down one of these properties, the fuzzier and more uncertain the other inevitably becomes. If you measure an electron's position with extreme accuracy, for instance, its momentum immediately becomes wildly uncertain, spreading out into a vast cloud of possibilities. Conversely, if you measure its momentum very precisely, its position instantly spreads out into a blur of probabilities. This is not a fault with your tools, nor is it a sign of technological clumsiness. It is a built-in feature of how the universe fundamentally operates on small scales. To see why, imagine describing a simple wave, which is what every quantum particle essentially is. If you want to define a wave's position precisely, you must use a combination of many different wavelengths, which necessarily means combining many different momenta. If you allow the wave's position to spread out, the wave becomes more uniform and its momentum becomes more definite. The inherent uncertainty between these two quantities is not about measurement errors. It is a trade-off written directly into the mathematics of waves. This profound idea forces us to abandon the comforting, but ultimately false, image of a particle as a tiny billiard ball with a well-defined position and a precise speed. At the quantum level, such simultaneous precision is absolutely impossible. Instead, a particle exists as a probability distribution, a gentle blur of possibilities that only partially sharpens when it is measured. You can think of it like trying to describe a melody while it is still playing. You can know the song's overall tempo, momentum, or the exact note being struck, position, but not both with total certainty at the instant you look. The act of narrowing one aspect necessarily blurs the other, a fundamental limitation imposed by the universe itself. This essential balance of knowledge extends beyond the pair of position and momentum. Other pairs of properties follow similar trade-offs. Energy and time, for example, are linked by an uncertainty relationship of their own. The shorter the time period you use to measure a system, the less precisely you can determine its energy. This seemingly odd limitation has powerful, far-reaching consequences. It is this principle that explains why energy can briefly borrow from the vacuum, why virtual particles can briefly appear and vanish in empty space without breaking any underlying physical laws. As long as these fluctuations occur quickly enough, they remain perfectly legal under the uncertainty principle. The universe, in a sense, allows itself tiny, temporary overdrafts of energy, provided they are repaid almost instantly. This inherent limitation might sound like a weakness, but it is precisely what gives the quantum world its structure and stability. Without uncertainty, atoms would be impossible. Electrons would spiral into their nuclei and all matter would collapse into a dense, featureless soup of pure energy. The uncertainty principle provides a kind of built-in cushion, a quantum pressure that prevents particles from occupying the same space too neatly. It is this gentle fuzziness that gives atoms their necessary size, shapes all chemistry, and prevents the universe from imploding. One of the most fascinating consequences of uncertainty is that it redefines what reality means. In classical physics, everything has definite properties whether or not we observe them. In quantum mechanics, many of those properties simply do not exist until they are measured. The particle doesn't secretly have a precise position and momentum waiting to be revealed. It genuinely lacks them until the act of measurement forces it to take on specific values. Observation doesn't just inform, it is a profound act of participation. This concept once unsettled even the pioneers of physics. Albert Einstein famously resisted the idea, insisting that God does not play dice. To him, uncertainty felt like an incomplete picture, a sign that quantum theory was missing some deeper, more deterministic truth. But decades of rigorous experiments have consistently shown that uncertainty is not a symptom of ignorance. It is the universe's own handwriting, its natural grammar for describing the very small. One might think this intrinsic randomness would lead to a chaotic universe, but the opposite is true. When viewed statistically, quantum uncertainty produces astonishing precision. The spread of possibilities follows exact mathematical rules, and those rules make crystal clear predictions. Lasers, atomic clocks, and transistors all depend fundamentally on the reliable nature of quantum uncertainty. If the world were perfectly deterministic, these technologies wouldn't work. It is the very fuzziness of the microworld that allows them to exist. This quantum pressure, born of the uncertainty principle, applies even at colossal scales. Inside white dwarf stars and neutron stars, for instance, uncertainty in momentum prevents matter from collapsing under gravity's relentless pull. When electrons are squeezed into impossibly small spaces, the exclusion principle and the uncertainty principle force their momentum to become increasingly uncertain and, on average, extremely high. This creates a pressure known as degeneracy pressure, a quantum force strong enough to hold up an entire star, thus helping to prevent the cosmos from crushing itself into oblivion. Uncertainty, therefore, is not the enemy of knowledge. It is the quiet, elegant architecture that makes the universe both stable and alive. Beneath the precision of our instruments and the predictability of our world lies a gentle blur, a built-in softness that keeps reality from collapsing under its own weight. And in that fundamental balance between what can be known and what forever remains uncertain, the universe finds its essential, enduring rhythm. We continue our quiet exploration of quantum uncertainty, moving from the relationship between position and momentum to an equally profound pairing, energy and time. Just as you cannot know where a particle is and where it is going simultaneously, you cannot know a system's precise energy if you only observe it for a fleeting, short duration. This fundamental link is the cornerstone of many bizarre and beautiful phenomena in the subatomic world, demonstrating how the irreducible blur of quantum mechanics is, paradoxically, the source of structure and stability. The energy-time uncertainty relationship states that the shorter the time period, a delta T dollar, you used to measure a quantum system, the less precisely, delta E dollars, you can determine its energy. Conversely, to know a system's energy with extreme accuracy, you must observe it for a long duration. This might sound like an odd mathematical limitation, but it has truly extraordinary consequences that shape the reality of empty space itself. This principle explains why energy can briefly borrow from the vacuum, and why particles can seemingly appear and vanish in empty space without immediately breaking the law of conservation of energy. The universe, in a sense, allows itself tiny, temporary overdrafts of energy, provided they are repaid almost instantly. These fleeting energy surges create particle-antiparticle pairs that pop into existence, live for unimaginably short times, and then annihilate, restoring the energy they borrowed. These are known as virtual particles. As long as these energy fluctuations occur quickly enough, they remain perfectly legal under the uncertainty principle. The shorter the lifetime of the borrowed particle, the greater the amount of energy that can be borrowed. This means the vacuum is far from the inert, silent void imagined by classical physics. It is an active, restless sea of potential, constantly fizzing with invisible, short-lived energy. This profound vacuum activity has direct, measurable effects. It explains the Lamb shift, a small, subtle discrepancy found when measuring the energy levels of electrons in hydrogen atoms. Classical quantum mechanics could not account for this tiny deviation, but the solution lay with the restless vacuum itself. The fluctuating electromagnetic field slightly perturbs the orbiting electron, nudging its energy just enough to be detected. This shift was one of the first. Clear, experimental pieces of evidence that the so-called empty space is, in fact, filled with quantifiable activity. Heisenberg's principle forces us to accept that the universe operates on a principle of trade-off. This limitation might seem like a weakness, but it is precisely what gives the quantum world its structure and its protective strength. Without the intrinsic fuzziness provided by uncertainty, atoms would be impossible. If electrons could simultaneously have a precisely known position and a precisely known momentum that allowed them to spiral inward, they would inevitably crash into the nucleus, and all matter would collapse into a dense, featureless soup of pure energy. The uncertainty principle, however, provides a kind of built-in cushion, a minimum fuzziness that prevents the particles from occupying the same space too neatly. This creates a quantum pressure that gives atoms their necessary size, shapes all chemistry, and keeps matter stable. It dictates the stable regions of probability, the quantized orbitals, where electrons reside. The electron is not whirling like a planet, but exists as a standing wave pattern, where the balance between the uncertainty in its position and the uncertainty in its momentum prevents it from collapsing inward. This is the simple yet profound reason that atoms endure and matter persists. Furthermore, this stability mechanism scales up to colossal sizes where it takes on a truly cosmic role. In the cores of dead stars, such as white dwarf stars and neutron stars, matter is squeezed to extreme densities by unimaginable gravitational pressure. The Pauli exclusion principle, which forbids two identical particles from sharing the same quantum state, forces electrons in white dwarfs or neutrons in neutron stars into higher and higher energy levels. The uncertainty principle then dictates that as these particles are localized into smaller and smaller spaces, their momentum becomes wildly uncertain and, on average, extremely high. This high momentum generates a force known as degeneracy pressure, a pure quantum pressure strong enough to resist the immense gravitational collapse of an entire star. In this way, Heisenberg's principle helps prevent the cosmos from crushing itself into oblivion. The fuzziness of the microworld is what holds up the most massive objects in the universe. The most fascinating consequence of uncertainty is that it fundamentally redefines what we mean by knowledge and reality. The uncertainty principle ensures that a particle does not secretly have a precise position and momentum waiting to be revealed. It genuinely lacks them until the moment of measurement. Observation does not just inform. It is an act of participation that forces the system to select a set of defined values, if only partially, from the original vast field of possibilities. This intrinsic randomness is not chaotic. It is a structured harmony that, when viewed statistically across countless particles, produces the astonishing precision necessary for all modern technology. Lasers, atomic clocks, and transistors rely on the predictable nature of quantum uncertainty. The universe does not promise certainties. It offers boundaries within which everything makes sense. The quantum world is not a map of fixed truths, but a guide to the likelihoods, the shapes of possibility, and in those shapes, An extraordinary, deep-seated order is found. Uncertainty is not the enemy of knowledge. It is the quiet, necessary architecture that makes the universe both stable and alive. Beneath the comforting precision of our macroscopic world lies a gentle, protective blur, a fundamental softness that ensures reality is not a rigid, deterministic script, but a continuous, balanced negotiation between the potential of energy and the flow of time. Measurement in the quantum world is one of those ideas that seems deceptively simple on the surface, but the deeper you look, the stranger and more profound it becomes. In classical physics, measurement is entirely straightforward. You observe something that already exists, like checking the temperature of a cup of tea or the speed of a car. The act of observation is passive. It records a fixed truth. But in quantum mechanics, the act of measuring doesn't just reveal what was there. It actively helps decide what becomes real, making the observer a necessary participant in the unfolding of reality. This is the participatory act that governs the transition from pure potential to concrete fact. Before measurement, a quantum system can exist in a superposition of possibilities. Its state encoded in the wave function, which represents all potential outcomes simultaneously. After measurement, however, only one single outcome remains. It is as if the universe flips a coin, but one that is weighted precisely according to the mathematical rules of quantum probability. When we measure a quantum system, we are effectively forcing it to choose from a set of potential states. The odds of each result are determined by something called the amplitude, a complex number describing how strongly that state contributes to the overall wave function. These amplitudes, as we've seen, can interfere with one another, adding and cancelling in ways that elegantly shape the probabilities we ultimately observe. When the measurement happens, the wave function collapses, or appears to collapse, into a single definite outcome, one instantaneous snapshot selected from the infinite film reel of potential stories. What is truly remarkable is that while any single, isolated measurement seems entirely random, the statistics of many repeated measurements are perfectly predictable. The randomness isn't chaotic, it's profoundly structured. Quantum theory doesn't tell us which individual event will occur, but it tells us the exact pattern that will emerge when billions of them do. It's like being able to predict the precise shape of a dice histogram. You can't know each individual roll, but you can know the average outcome with exquisite accuracy. This statistical precision is what gives quantum mechanics its enormous power. The numbers it predicts match experiments to astonishing degrees, often to more than 10 decimal places. This probabilistic nature, however, led to one of the most famous and passionate debates in the history of science. Albert Einstein struggled fiercely with the idea that nature itself might be fundamentally random, famously declaring, "God does not play dice." To him, quantum mechanics was incomplete. Its probabilities reflected our ignorance, not the universe's intrinsic uncertainty. But decades of rigorous experiments have consistently shown that Einstein's hope for hidden variables, unknown factors that predetermine the outcome, was ultimately in vain. The randomness appears to be real, intrinsic, and irreducible. The universe truly does play dice, but with a consistency that is the very definition of natural law. The measurement process also fundamentally blurs the line between the observer and the observed. In everyday life, we imagine these as entirely separate. The scientist looks through the microscope and the world sits passively on the slide. But quantum physics does not allow for such a clean distinction. To measure a particle, you must inevitably interact with it, and that interaction fundamentally changes it. The photon you use to see an electron transfers energy and momentum, disturbing the very thing you are trying to examine. The observer, or more accurately, the measuring device, becomes an inextricable part of the experiment. The measuring device becomes entangled with the system. After measurement, they are no longer independent. They share information in a single, unified, combined state. This profound realization inspired endless debate among the founders of quantum theory. Niels Bohr argued that we can never speak about a system's properties in isolation, only about the outcomes of measurements. Reality, he suggested, doesn't exist as definite values before we observe it. Instead, it exists as potentialities that only solidify into fact through interaction. Others, like Schrödinger, found this view deeply unsettling, leading to the absurd dramatization of his cat being in limbo until an observer opens the box. Over time, physicists began to realize that the key to understanding measurement lies in the process of decoherence. Decoherence describes how quantum systems lose their delicate superpositions when they interact with their environment.
Every tiny collision, every flicker of heat, every vibration leaves a trace, entangling the system with the surrounding world.
The result is that the interference patterns characteristic of quantum behavior disappear almost instantly, and the system still obeys quantum laws, but its superpositions become inaccessible, buried in the complexity of countless microscopic interactions. To us, it simply looks classical. Decoherence explains why tables don't exist in two places at once, why cats appear either alive or asleep, and why the macroscopic world seems stable and predictable. It bridges the gap between the quantum and the everyday without requiring any mystical collapse. What makes measurement even more fascinating is that we can see its effects in controlled, time-sensitive experiments. Physicists can perform so-called delayed choice experiments, where they decide whether to observe a particle as a wave or a particle after it has already passed through the apparatus. Somehow, the particle's behavior still aligns with the choice, as if reality adjusts retroactively to fit the observation. This doesn't mean the future changes the past, but it does mean that the concept of a definite fixed history, something classical physics takes for granted, starts to unravel at the quantum level. The universe seems to keep its options open until the very end, and what counts as a measurement depends entirely on what information remains accessible to the environment. In the end, measurement in quantum mechanics teaches a quiet but fundamental lesson about participation. The universe doesn't unfold as a static film reel waiting to be watched. It is an active conversation between systems, each probing and influencing the other. Reality at its smallest scales isn't a fixed script. It's a series of negotiations written in probabilities and read through interaction. When you look closely enough, even the simplest question, "What happened?" turns out to depend entirely on how, when, and whether you chose to ask. And in that subtle dependence, somewhere between possibility and fact, lies the strange, elegant balance that allows the universe to be both unpredictable and perfectly consistent all at once. The final piece of the puzzle regarding quantum measurement and the stability of our world lies in understanding the gentle, ceaseless process known as decoherence. We have explored how quantum systems exist in a state of superposition, maintaining perfect coherence, or phase synchronization, where multiple possibilities coexist. The obvious question remains: why does the macroscopic world of tables and chairs look so classical, so predictable, if it is built from probabilistic quantum parts? The answer is that this delicate quantum order, this coherence, is almost instantaneously destroyed by the environment, transforming potential into fact. This is the transition from coherence to fact. In simple terms, decoherence describes how a quantum system loses its delicate superposition when it interacts with its surroundings. It is not an act of destruction in the ordinary sense. It is more accurately described as a process of information leakage and entanglement. Every quantum system exists in superposition until it becomes irrevocably entangled with the noisy world around it, spreading its fragile quantum information into countless surrounding particles. Every tiny collision with a stray air molecule, every flicker of heat, every vibration of the atoms in the environment leaves an indelible trace, robbing the system of its unified quantum rhythm. Once this information is dispersed, it is practically impossible for the original system to recover or exhibit its coherent, wave-like nature. The interference patterns that are the hallmark of quantum behavior disappear almost instantly. The system still obeys quantum laws, but its superpositions become entirely inaccessible, buried in the sheer complexity of countless microscopic interactions. To us, the macroscopic observer, the system appears to have instantaneously and definitively collapsed into a single, fixed outcome. Decoherence, therefore, is the quiet, elegant process that bridges the gap between the quantum realm and our stable, everyday experience, offering a seamless, physical explanation for why the world appears classical. This process explains why macroscopic objects like a baseball or a human being appear to be in one place at one time. Their interaction with the hot, noisy world is so frequent and overwhelming that coherence disappears in a time frame far too brief for us to perceive, often in less than a trillionth of a second. The boundary between the quantum and classical worlds is not, in this view, marked by size or mass, but by isolation. The more effectively a system can be shielded from environmental noise, the longer it remains coherent, and the longer it exhibits its strange quantum properties. This need for isolation is why engineers building quantum computers go to extraordinary lengths, cooling their systems to near absolute zero and encasing them in layers of shielding. They are constantly fighting the universal tide of decoherence. Crucially, decoherence provides a far more grounded interpretation of the observer's role in quantum mechanics than the original, perplexing notion of an observer-induced wave function collapse. Rather than invoking a mysterious, ill-defined role for consciousness, decoherence shows that the collapse is purely a physical interaction. The key is not who observes, but that an observation or any information-transmitting event takes place. Whether the system interacts with a scientist's eye, a photographic plate, or a stray dust particle, the effect is the same. The delicate phase relationship is scrambled, and the superposition is irreversibly destroyed.
The observer is not a magical entity, but a necessary
piece of physical apparatus that forces the quantum choice. This understanding is particularly important when considering mind-bending experiments like the delayed choice setup. In these experiments, the decision to measure a particle as a wave or a particle is sometimes made after the particle has already passed through the experimental apparatus. The particle's behavior, strangely, still aligns with the later choice. Decoherence explains that the particle does not defy time, but that the coherence of the quantum system is maintained across a greater spatial distance than previously thought. The information about all possible paths remains available to the wave function until the very final, unavoidable interaction with the macroscopic world forces the definitive choice. Reality does not decide its past until the coherence is finally lost, an elegant and profoundly subtle distinction. The effect of decoherence is so ubiquitous and relentless that it is a constant background factor in virtually every physical process. Even though atoms and molecules are built from quantum parts, the sheer number of particles involved in a larger object means the probability of a fully coherent state being maintained is virtually zero. Decoherence ensures that the probabilities of a quantum state blur rapidly into the averages we call facts, resulting in the stable, predictable outcomes necessary for classical reality. Without this constant loss of coherence, the world would remain a permanent, chaotic blur of possibilities, never settling into the stable patterns we rely on. In the language of information theory, decoherence is a process that renders quantum information inaccessible. The total quantum information of the universe is still conserved, but the specific information contained within a local superposition is quickly dispersed into the complexity of the environment. The other possibilities, the alternate realities, don't necessarily vanish. They are simply woven into patterns too subtle and too vast for us to ever detect or retrieve. Our experience of reality as a single, fixed narrative is therefore a direct result of our inability to perceive the complex, widespread entanglement created by decoherence understanding. Decoherence is crucial not just for physics but for technology. The greatest challenge facing quantum computing, as noted, is battling this environmental noise. Engineers must find ways to shield and correct errors constantly to keep those fragile quantum phases intact long enough to perform meaningful work. Furthermore, this knowledge provides a clearer philosophical perspective. The world does not stop being quantum simply because it looks classical. It remains quantum. It just becomes too entangled with itself for the strangeness to stand out. Decoherence simply hides quantum mechanics by transforming the quantum blur into the classical average. In the most profound sense, measurement is not an abrupt, mystical event, but a seamless transition from a coherent superposition to a state of complex correlation with the environment. It is the moment when possibility becomes a statistically weighted fact. The quantum world doesn't hand us certainty. It simply offers boundaries within which everything makes sense, transforming the universe from a confusing set of probabilities into the precise, predictable cosmos we experience every day. The balance between coherence and decoherence is the essential rhythm of existence. Entanglement is one of those ideas that feels like it was smuggled into physics straight from a science fiction story. It describes a connection so deep that two particles, once linked, seem to share a single state, no matter how far apart they travel. Change one, and the other responds instantly, not through space but beyond it, as if the concept of distance has been quietly erased from their shared existence. Albert Einstein famously called this eerie phenomenon spooky action at a distance, a phrase that perfectly captures both his deep skepticism and the profound, almost supernatural elegance of the effect. To truly picture entanglement, imagine a quantum process that creates a pair of particles whose properties are perfectly correlated. For example, imagine two electrons are produced in such a way that their total spin must always add up to zero. If one electron is measured to be spinning up, the other electron, instantly, regardless of its location, must be spinning down. When these two particles separate, perhaps traveling to opposite ends of the galaxy, each particle, individually, carries no definite spin of its own. It is only the relationship that ties them together that is certain. Measure one, and the state of its partner becomes known instantly, even if it is light years away. This is not communication, because no usable signal travels between them, but it is an astonishing display of quantum unity, the idea that two objects can share a single, inseparable identity. The truly strange part is that until the moment of measurement, neither particle possesses a definite value. They exist in a superposition of possibilities bound together by their shared wave function. When one is measured, the joint state collapses and both results become real in perfect opposition, fitting flawlessly with its partner. This phenomenon completely defies our classical intuition, which insists that information must move through space and time at a finite speed, a speed limited by the velocity of light. In quantum mechanics, however, it is as if the two particles are simply aspects of the same single system, their fundamental connection not limited by the vastness of space. Physicists spent decades passionately arguing about whether these uncanny correlations were truly non-local, existing
instantaneously beyond space and
time, or were simply the result of hidden variables, unknown, local factors that predetermined the outcomes in a way we couldn't detect. Einstein, Boris Podolsky, and Nathan Rosen famously raised this challenge in a 1935 paper, suggesting that quantum mechanics must be incomplete. If the theory allowed such instantaneous effects, they reasoned, it couldn't fully describe reality as it truly is. Something deeper, some hidden deterministic mechanism, must be missing. The challenge to Einstein's skepticism was finally formalized by John Bell, an Irish physicist who in the 1960s formulated a way to experimentally test this philosophical disagreement. Bell derived mathematical inequalities, strict limits on how strong correlations could possibly be if local hidden variables were responsible. If experiments could ever show correlation stronger than those limits, it would mean that no local, deterministic explanation could possibly account for them. The quantum prediction would have won, and when the definitive tests were finally performed, starting with the pioneering experiments of Alain Aspect in the 1980s and continuing with ever more precise and demanding setups. The results were clear. The quantum predictions were correct. The observed correlations were stronger than any local theory could allow. Nature, it seems, genuinely defies classical separation. Crucially, entanglement does not mean that information travels faster than light. The results of measurements are still fundamentally random. No observer can control which outcome, spin up or spin down, appears. Therefore, no usable signal can be sent through the connection. But once both results are compared, the correlations emerge, synchronized with mysterious perfection. The randomness of each individual result remains untouched, yet the total result is flawlessly linked to its partner. This is not about messages traversing space. It is about space itself not being the whole story. What's truly remarkable is that entanglement isn't rare or fragile. It is absolutely ubiquitous. It happens naturally in atoms, molecules, and light beams. It is the invisible glue that holds much of quantum mechanics together. In fact, entanglement can be thought of as the currency of the quantum world, an invisible thread that allows systems to share information in ways classical physics can never match. Far from being a mere philosophical curiosity, it is now an indispensable tool that engineers and scientists use deliberately every day. Quantum communication relies on entanglement to ensure perfect security. In quantum key distribution, two distant parties share pairs of entangled photons. If anyone tries to eavesdrop, the act of measurement disturbs the system, immediately breaking the correlations and revealing the intrusion. This system does not rely on complex mathematical puzzles for security. It relies on the inviolable physical law that observation changes the outcome. Quantum computers, too, depend critically on entanglement. By linking quantum bits, or qubits, through entanglement, operations on one qubit instantly influence the probabilities of others, enabling patterns of computation that are impossible for classical machines. It is this profound interdependence, this subtle dance of correlated states, that grants quantum computers their extraordinary potential power. Entanglement is the essential structure that links the computational possibilities together. Entanglement also plays a quiet, essential role in the natural world. In photosynthesis, for instance, it may help plants transfer energy with near-perfect efficiency by keeping multiple molecular pathways correlated. In physics research, entangled particles are used constantly to test the limits of relativity, to measure minute gravitational effects on quantum systems, and to probe the fundamental symmetries of the universe. Even the physics of black holes may owe their connection to the quantum fabric of space-time itself, with entanglement acting as the stitching that holds the cosmos together. Entanglement forces us to profoundly rethink what it means for two things to be separate. The concept of locality, the idea that objects can only influence each other through contact or signals traveling between them, breaks down entirely. The universe at its deepest level seems less like a collection of independent objects and more like a single, continuous web of correlation. Each particle, each atom is a node in that web, its properties defined as much by its relationships as by its individual existence, and yet, for all its philosophical weight, entanglement behaves with perfect obedience to the equations that describe it. It is not a loophole or a contradiction. It is the natural outcome of quantum theory's precise mathematics. The correlations are strong, but never exploitable for instant messaging. Mysterious, but never chaotic. Nature allows connection without communication, coordination without contact, and certainty without cause. What once seemed supernatural has become a daily, predictable tool in laboratories around the world. Entanglement, far from being an embarrassment to our understanding, is a silent, enduring testament to how deeply unified the universe truly is. When two particles meet and part ways, they never fully let go of each other. Some invisible bond remains, woven into the laws of probability themselves. It's as though the universe keeps a quiet record of their meeting, an echo of shared existence that distance can't erase. In that subtle, unbreakable connection lies one of the most extraordinary truths of all: that separation at the smallest scales is often an illusion. The eerie elegance of entanglement, which Albert Einstein famously dubbed spooky action at a distance, created one of the deepest philosophical fissures in the history of science. For decades, the debate raged: were the perfect correlations observed between entangled particles truly instantaneous and non-local, or were they merely the result of hidden variables, unknown factors that secretly predetermined the outcome of each particle locally, ensuring they matched when later compared? This question struck at the heart of quantum mechanics, challenging its completeness and its very description of reality. It was a challenge that required moving beyond abstract argument and into the realm of precise experimental physics. An Irish physicist, John Bell, picked up the philosophical gauntlet in the 1960s. Bell recognized that while the philosophical debate was intractable, the mathematical difference between the two possibilities, non-local quantum effects versus local hidden variables, could be rigorously tested. He formulated what are now known as Bell's inequalities, a series of mathematical limits. These limits established how strong the correlations between two distant particles could possibly be if their outcomes were predetermined by any physical mechanism acting locally. Any theory that insists on locality, the idea that an object can only be influenced by its immediate surroundings, must obey these inequalities. Bell's work was revolutionary because it transformed an abstract philosophical dispute into a concrete experimental test. If experiments could ever show correlations between entangled particles that were stronger than the upper bounds set by Bell's inequalities, it would mean that no local, deterministic explanation, no hidden variable theory, could possibly account for them. The quantum prediction would have won, proving that non-local effects, the spooky action, are real and fundamental to nature. The definitive experimental tests began in earnest in the 1980s. Pioneered by physicists like Alain Aspect and his team, they meticulously designed apparatuses to measure the polarization of entangled photons separated over significant distances, ensuring no classical information could pass between them. The results were stunningly clear, and they have been confirmed by ever more precise and demanding experiments since. The correlations observed in the entangled particles were indeed stronger than Bell's inequalities allowed. The quantum predictions were correct, demonstrating that nature truly does defy classical local separation. This confirmation of non-locality fundamentally reshaped our understanding of the universe. It showed that when two particles are entangled, their connection is not limited by the fabric of space and time. They exist as aspects of a single system, their fates instantly interwoven, regardless of the vast physical distance separating them. This is the profound concept of shared identity. The properties of the whole system are more fundamental than the individual properties of the parts. When you measure one, you are not sending a signal to the other. You are collapsing the unified wave function that describes both simultaneously. It is important to emphasize that this quantum win does not mean information travels faster than light, thereby violating Einstein's theory of special relativity. The individual results of the measurements remain inherently random. An observer cannot control whether a photon lands as spin-up or spin-down. Therefore, no observer can exploit the connection to send a directed message or signal to the distant partner faster than light. The instantaneous effect is on the correlation, the pattern, not on the usable conscious transfer of information. The randomness of each individual measurement preserves the light speed limit, yet the total result, the combined synchronized pattern, is mysterious and immediate. It is a subtle but crucial distinction that allows quantum mechanics and relativity to coexist, albeit uncomfortably. This astonishing display of quantum unity has moved far beyond philosophical inquiry. It is now the essential foundation for a range of new technologies. Entanglement is the vital currency of the quantum world, allowing systems to share information in ways impossible for classical physics. For example, quantum cryptography relies entirely on Bell's confirmation. In systems utilizing quantum key distribution, any attempt by an eavesdropper to measure the entangled photons instantly disturbs the correlation, exceeding the limits set by Bell's mathematics and alerting the users to the intrusion. Security is no longer based on the difficulty of solving a complex mathematical puzzle, but on the inviolable laws of physics themselves, which guarantee that observation cannot be passive. Furthermore, quantum computation fundamentally depends on the ability to entangle multiple qubits, linking them into a massive single computational state. Operations on one qubit instantly affect the probabilities of others, enabling the system to process information in a parallel, interconnected web that grants it extraordinary power. The quantum computer utilizes the statistical harmony of these non-local correlations to sculpt the probability landscape, reinforcing the correct answers while cancelling the incorrect ones. The continued pursuit of closing the loopholes in Bell's tests experimental setups designed to rule out any remaining possibility of local effects has only cemented the initial findings. Experiments have successfully entangled photons, electrons, atoms, and even large molecules, sometimes across distances of hundreds of kilometers, and have shown the quantum correlation surviving the vast turbulent void between the Earth and orbiting satellites. Bell's theorem, and the subsequent experiments that validated it, represents one of the most profound lessons in the quantum journey. It taught us that the universe at its deepest level is not a collection of isolated, independent objects governed by local forces. It is instead a single, continuous, interconnected web where separation is often an illusion. When two particles share a beginning, they share a shared identity that distance cannot erase, their fates forever linked by a bond woven into the laws of probability themselves. The spooky action is simply the natural behavior of reality when viewed through the uncompromising lens of quantum correlation. Spin is one of those concepts in quantum mechanics that sounds simple by name but becomes profoundly complex when you try to explain what it actually is. The name suggests that subatomic particles are physically rotating like tiny planets, but that classical picture is deeply misleading. Spin is not motion through space. It is an intrinsic property, a kind of permanent, built-in angular momentum that doesn't rely on any physical rotation of the particle itself. If an electron were truly spinning in the classical sense, its surface would have to move faster than the speed of light to produce the measured angular momentum, which is impossible according to relativity. Yet the particle behaves precisely as if it carries a permanent internal twist. Spin is one of nature's most subtle fingerprints, an invisible arrow built into every quantum object. The discovery of spin dates back to the early 1900s, when physicists noticed a strange, unexpected doubling in certain atomic spectral lines. According to the best models of the time, transitions between specific energy levels should have produced single, precise lines of light, yet they appeared as distinct pairs. In 1925, two young Dutch physicists, George Uhlenbeck and Samuel Goudsmit, proposed that electrons must possess an intrinsic angular momentum, something distinct from their motion around the nucleus. Their bold idea explained the puzzling patterns instantly and revealed an entirely new, fundamental dimension of quantum behavior. Unlike ordinary angular momentum, which can take on any continuous value depending on how fast or slow an object rotates, quantum spin comes in discrete chunks. It is quantized, meaning it can only take on specific, fixed values, often expressed in multiples of Planck's constant. This quantization is a rigid rule of the quantum world. Electrons, protons, and neutrons, the fundamental components of matter, each possess a spin of $1–2, a half-integer spin, while photons, gluons, and other force-carrying particles have integer spin, such as 1 or 2. This fundamental difference divides the universe into two great families: fermions, which have half-integer spin and make up all matter, and bosons, which have integer spin and carry the forces that act between the particles. Spin also comes with a curious, almost mind-bending rule known as the two-turn symmetry. When you rotate an ordinary macroscopic object by 360 degrees, it returns exactly to its original starting condition. However, if you conceptually rotate an electron's quantum state by 360 degrees, it does not come back to its original form. It acquires a negative sign, a change in its quantum phase. Only after a full 720-degree rotation does it finally return to its starting condition. This bizarre two-turn symmetry defies all classical logic, yet it is a deeply verified property that lies at the heart of the mathematics describing all fermions. It is the signature of the half-integer nature of the particle. One of the most elegant and famous demonstrations of spin came from the Stern-Gerlach experiment in 1922. Otto Stern and Walter Gerlach sent a beam of neutral silver atoms through a non-uniform magnetic field. Classical physics predicted that the atom's tiny magnetic moments would orient randomly, producing a continuous elongated smear on the detector. Instead, the beam split cleanly into two distinct spots. The silver atoms, each containing a single unpaired electron, could only have two possible orientations of spin, up or down, with absolutely nothing in between. This result shocked the scientific community, providing undeniable proof that spin, like so many other quantum quantities, doesn't vary smoothly but jumps between fixed, discrete states. This inherent two-state nature of spin makes it an ideal candidate for storing information. In fact, modern quantum computers often use the spin of electrons, atomic nuclei, or photons as qubits, the quantum equivalents of classical bits. A spin qubit can exist in a superposition of both up and down simultaneously, vastly expanding the computational landscape. By entangling multiple spins, quantum computers can perform calculations that would take classical machines longer than the age of the universe. Spin is also deeply, fundamentally tied to magnetism. Every electron acts like a tiny bar magnet because of its spin. In most everyday materials, these little magnetic moments point in random directions, cancelling one another out. But in ferromagnetic substances like iron, the spins of countless electrons align in the same direction through powerful quantum interactions. When large regions of aligned spins form, they create magnetic domains. When those domains line up, we get the familiar magnetism strong enough to hold a note to a refrigerator door. The magnetism we experience every day, from compasses to hard drives, is simply quantum spin made visible and scaled up. The role of spin extends far beyond magnets. It shapes chemistry itself. When two electrons occupy the same orbital in an atom, they must have opposite spins. This strict rule, known as the Pauli exclusion principle, arises directly from the fact that electrons are fermions. No two fermions can share the exact same quantum state. The exclusion principle is what explains why atoms have structure, why matter takes up volume, and why the periodic table exists in its layered complex form. Without spin, electrons would collapse into the lowest energy level, and all of chemistry would instantly vanish. Spin even plays a crucial role in the light that reaches your eyes. Photons, the carriers of electromagnetic radiation, have a spin of 1. Unlike electrons, their spin is aligned with their direction of motion, producing what we call polarization. When you wear polarized sunglasses, you are interacting with spin on a macroscopic scale, filtering light based on its spin orientation to reduce glare. Every time you tilt your head and watch the light change, you are engaging with quantum spin. In particle physics, spin acts as a kind of cosmic classifier, determining not only what a particle is but also how it behaves. Fermions build the material world by stacking in complex ways, while bosons mediate forces, allowing fermions to communicate their presence. The recently discovered Higgs boson has spin 0, giving it a unique ability to endow other particles with mass. The photon's spin makes electromagnetism work. Spin is truly the hidden arrow, an intrinsic quantum compass inside every particle, guiding its behavior, dictating its interactions, and giving rise to nearly every magnetic and structural feature of matter. From the smallest electrons in an atom to the colossal magnetic fields of planets and galaxies, this same precise principle repeats. The intrinsic quantum property of spin, which we've established is not a physical rotation, but a fundamental internal twist, has consequences that reach out from the subatomic scale to shape the world we experience every day. It is the hidden mechanism that creates the invisible forces of magnetism and dictates the very structure and volume of matter. This is the story of magnetism made visible, revealing how spin and the strict rule it obeys, the Pauli exclusion principle, build reality with a precision that defies intuition. As we discovered, every electron acts like a tiny bar magnet because of its spin. In most materials, the magnetic moments associated with these tiny spins point in random directions, effectively cancelling one another out. But in ferromagnetic substances such as iron, cobalt, and nickel, the collective behavior of the electrons is governed by powerful, non-local quantum interactions known as exchange forces. These forces cause the spins of countless electrons to align in the same direction over large regions, creating magnetic domains. When those domains line up, when trillions of electrons point their invisible arrows in unison, we get the familiar, strong magnetism that can hold a note to a refrigerator door, lift scrap metal, or guide a compass. That common, palpable force we experience is simply quantum spin scaled up and made visible. The fundamental physics behind every magnet on Earth is rooted in the synchronized quantum behavior of microscopic,
non-physically spinning particles. The profound influence of spin extends far beyond magnets, as it is the key ingredient in one of the most vital rules in nature, the Pauli exclusion principle.
This principle, formalized by the physicist Wolfgang Pauli in 1925, arises directly from the fact that electrons are fermions, particles with half-integer spin. The principle states, with absolute certainty, that no two identical fermions can occupy the same quantum state simultaneously. If one electron in an atom sits in a particular energy level with a specific orbital motion and a specific spin orientation, say, spin up, no other electron can possess that exact same combination. This simple, antisocial rule of the quantum world is what sculpts the entire architecture of everything around us. It is the reason why electrons fill atoms in distinct, layered shells, rather than all collapsing into the lowest energy state, as they would if they were bosons, integer spin particles, which enjoy sharing states. Every additional electron must find its own unique configuration of quantum numbers, creating the shells and subshells that determine how atoms bond and form molecules. The incredible diversity and complexity of the periodic table, the core of all chemistry, stems entirely from how electrons are forced to stack up according to the Pauli exclusion principle. Furthermore, Pauli's rule is the reason you cannot walk through walls. When you press your hand against a solid surface, the repulsion you feel is not merely a direct, mechanical push. It is, at its deepest level, a quantum force. The electrons in your skin are prevented from occupying the same space as the electrons in the solid object. The exclusion principle dictates that the electrons cannot overlap their quantum states, creating a kind of quantum pressure that resists compression. The fundamental solidity of matter, the sensation of touch itself, is a direct, macroscopic consequence of fermions refusing to overlap. Without the rigid adherence to the exclusion principle, all electrons would collapse, atoms would shrink into nothing, and the sensation of being solid would vanish. This profound quantum behavior has been harnessed by modern medicine in one of its most important diagnostic tools, magnetic resonance imaging, or MRI. The MRI scanner exploits the subtle quantum property of spin in the nuclei of atoms, particularly the hydrogen atoms abundant in the body's water molecules. When a patient is placed inside the strong magnetic field of the scanner, The spins of these hydrogen nuclei align themselves much like trillions of tiny compass needles. A carefully timed pulse of radio waves, a form of precisely tuned electromagnetic energy, then knocks these nuclear spins out of alignment. As the spins relax and snap back into their original alignment, they emit faint radio signals. The scanner's detectors pick up these signals, and by mapping how the relaxation time varies across different tissues, which contain different amounts of water and, therefore, hydrogen, the machine builds detailed, three-dimensional images of the body's soft interior without a single incision. The clarity and resolution of those scans, down to fractions of a millimeter, come directly from the predictable, reliable quantum behavior of these nuclear spins in magnetic fields. The same physics that powers a simple refrigerator magnet is, through this intricate application, powering one of medicine's most vital technologies, allowing us to listen to the quiet, synchronized hum of the body's atoms. The elegance of this system is that it unites the small-scale rule with the large-scale effect. The spin of a single electron dictates magnetism, the spin of countless electrons dictates chemistry, and the spin of atomic nuclei dictates medical imaging. From the microscopic magnetic moment of a single electron to the complex structural stability of the periodic table, and finally, to the detailed, non-invasive internal images of the human body, the property of spin and the strict quantum rule it enforces are quietly, seamlessly woven into the fabric of reality. It is a striking testament to how the most subtle, abstract principles of quantum mechanics can yield the most tangible and visible consequences in our world. Every single particle in the universe belongs to one of two great families, an essential division that defines nearly everything about how matter and energy behave. These two families, fermions and bosons, are not distant cousins. Rather, they are the two fundamental complementary species in the quantum census, one building the solid structure of existence and the other weaving the forces that connect it all. They obey profoundly different rules, and those rules are what make atoms stable, light coherent, and the cosmos as structured and complex as it is. Fermions are the individualists of the quantum world. Electrons, protons, neutrons, and quarks, all the particles that make up matter, each staunchly refuses to share its exact quantum state with another. This strict, unyielding rule is the Pauli exclusion principle, named after the physicist Wolfgang Pauli. It states that no two identical fermions can occupy the same quantum state simultaneously. If one electron in an atom sits in a particular energy level with a specific spin, no other electron can take that exact combination. This simple, antisocial mandate shapes the entire architecture of everything around us. It is why electrons fill atoms in distinct layered shells, why elements have distinct chemical properties, and why matter takes up volume. Without this principle, all electrons would collapse into the lowest energy level, atoms would shrink into nothingness, and chemistry as we know it would vanish in a puff of energy. This refusal to share gives rise to the incredible complexity of the periodic table. Every additional electron must find its own unique configuration, creating the subtle differences between hydrogen, helium, carbon, and oxygen. The very solidity of matter, the sensation of touch itself, is a direct consequence of this fundamental quantum rule. When you press your hand against a table, the electrons in your skin are repelling the electrons in the wood, not because of a direct mechanical push, but because the quantum rules simply forbid them from overlapping in the same space. The matter-building particles, the fermions, are therefore responsible for the rigidity and resistance to compression that defines our everyday world. They follow what is known as Fermi-Dirac statistics, which mathematically forbids duplicates in the same state. Bosons, on the other hand, are the extroverts of the particle world. They don't mind sharing states. In fact, they prefer it, and they are the carriers of forces. Photons, which carry the electromagnetic force, gluons, which carry the strong nuclear force, and the Higgs boson, which gives mass to particles, are all bosons. Unlike fermions, multiple bosons can pile into the exact same quantum state, reinforcing one another's presence. This tendency to bunch together is what gives rise to some of the most remarkable and visually distinct phenomena in nature. Take the phenomenon of light, for instance. When many photons of the same frequency and phase travel together, they create a coherent beam, a laser. The process of light amplification by stimulated emission of radiation relies entirely on the basic behavior of bosons. Inside a laser, excited atoms are coaxed into emitting photons that are perfectly synchronized with those already present. Because photons are bosons, there is no restriction on how many can occupy the same state, so they cascade together, amplifying one another in perfect unison. The result is an intense, narrow, coherent beam of light capable of reading data from a disk or guiding a spacecraft millions of kilometers away. Without the cooperative nature of bosons, the concept of a laser would be utterly impossible. Bosons follow Bose-Einstein statistics, which encourages them to congregate. This fundamental difference, fermions keeping their distance, bosons clustering together, extends to the structure of the universe itself. The behavior of fermions gives matter its stability and resistance to compression, acting as a powerful quantum counterbalance. It is the fermionic pressure that keeps white dwarf stars from collapsing under gravity. Meanwhile, bosons weave the forces that connect those particles. They are the mediators of communication. Photons allow charged particles to interact. Gluons hold atomic nuclei together, and the graviton, if it exists, would carry the gravitational force through space-time. Bosons do not obey the exclusion principle because they do not matter in the conventional sense. They are the pure threads of interaction, the fundamental fields that connect everything else. The distinction between these two families isn't arbitrary. It comes down entirely to spin, that intrinsic quantum twist each particle carries. Fermions have half-integer spin values, like 1 $2 or 3 $2, while bosons have whole number spins, such as 0 or 1. That single difference changes the mathematical symmetry of their wave functions and dictates whether particles repel or congregate. It is not a personality trait, but a deep, unchangeable rule of nature built into the fabric of quantum statistics. The bosonic crowding also leads to another marvel, the Bose-Einstein condensate, BEC. When a gas of bosonic atoms is cooled to near absolute zero, the particles lose their individual identities and collapse into a single quantum state, behaving like one giant, unified atom. This state, first created in laboratories in 1995, is a profound expression of bosonic cooperation, a state of matter where the quantum world becomes visible on a macroscopic scale, with atoms marching in perfect synchrony. In the quantum world, these two species, fermions and bosons, complement each other perfectly, creating a sublime, essential duet. Fermions create the universe's stuff through their refusal to overlap, while bosons choreograph its behavior through their tendency to share. One builds structure through refusal, the other builds harmony through sharing. Their interplay is what gives rise to every physical phenomenon, from the rigidity of rock to the warmth of sunlight. Without fermions, there would be no matter. Without bosons, matter would never know how to interact. The entire structure of existence emerges from the ceaseless, quiet negotiation between particles that insist on individuality and those that thrive on unity. Every element, every burst of light from a distant galaxy is a quiet duet between these two fundamental families, each following its own timeless, elegant rule. In the modern view of physics, everything we observe, every particle, every force, every flicker of energy is ultimately an expression of something deeper and more pervasive: fields. This profound concept replaces the simple notion of particles as tiny dots zipping through empty space with the grand vision of the symphony of fields. where reality is a continuous dynamic tapestry of interwoven vibrations that fill all of space, rippling and interacting everywhere at once. A field is not a physical substance confined to a location. Rather, it is a kind of invisible, energetic presence spread throughout the entire universe. And what we commonly call particles are, fundamentally, not standalone objects, but quantized disturbances in those fields, tiny, stable ripples that behave like discrete bits of matter or light. Consider light itself. It is not a stream of miniature bullets racing through the void, but a wave in the electromagnetic field. That field exists everywhere, even in absolute darkness, vibrating with a quiet potential energy that can spring into motion when energy is added. A single photon is the smallest possible stable vibration of this field, a packet of energy with just enough amplitude to be counted as one unit. Every beam of sunlight, every radio wave, every color you have ever seen is made of countless electromagnetic ripples rising and falling in concert across the vastness of space. Matter follows this same profound rule. Electrons, protons, and quarks, the fundamental building blocks of atoms, are not standalone objects drifting through space, but excitations in their own underlying fields. There is an electron field that spans the entire universe, and every electron everywhere is simply a localized excitation within that single, pervasive field. When you hold up your hand, the electrons making up your skin are just tiny, confined peaks in the same vast field that stretches all the way to the edge of the cosmos. They look and feel distinct because the excitations are stable and confined, like the plucked, sustained notes of a tightly tuned instrument. Each type of fundamental particle has its own field, one for electrons, another for quarks, others for neutrinos, and so on. Similarly, the forces are carried by fields. The photon field carries electromagnetism. The gluon field binds quarks together inside protons and neutrons. And there is a field for the weak nuclear force, and even for the Higgs boson, whose pervasive field gives mass to other particles by resisting their motion through it. These fields do not switch off when nothing seems to be happening. They are perpetually present, quietly interacting and shaping reality beneath the surface of our perception. The interactions between particles, what we usually call forces, are simply exchanges of energy between these fields. When two electrons repel each other, it is not because invisible hands push them apart. It is because they disturb the electromagnetic field in each other's vicinity, and the field responds by transferring momentum via photons, the quanta of the electromagnetic interaction. When a quark feels the strong nuclear force, it is exchanging gluons, the quanta of the gluon field, with its neighbors. The same logic applies everywhere. Every fundamental force arises from fields talking to one another, passing information through their ripples and excitations. One of the most fascinating consequences of quantum field theory is that the vacuum itself, the so-called empty space between particles, is not empty at all. Even when stripped of all matter and energy, the fields remain. Quantum mechanics dictates that they cannot sit perfectly still. Instead, they tremble with restless zero-point energy, their values fluctuating randomly at every single point in space. Particles can briefly appear and disappear in these fluctuations, borrowing energy from the vacuum before fading away. These are called virtual particles. While they cannot be observed directly, their effects are measurable, confirming that the vacuum is far from inert. This something-from-nothing behavior is essential to the quantum world's stability and has real consequences, such as giving rise to the Casimir effect. The elegance of the field concept is that it fundamentally unites all particles and forces under one mathematical framework. In classical physics, we had separate rules for matter and for energy, for waves and for particles. Quantum field theory merged them into a single language. Matter is a form of energy, Waves are a form of particle. The difference lies only in how the field vibrates. High-energy, high-frequency vibrations manifest as massive particles, while gentle oscillations show up as light or radiation. The entire universe becomes a seamless symphony of interacting fields, its complexity built from simple harmonies that play across all of space-time. Even the concept of identity changes in this picture. When two electrons collide and scatter, there is no meaningful way to say which one is which afterward. They are indistinguishable excitations of the same underlying field. In a deep, profound sense, there is only one electron field endlessly rippling, and every electron we ever detect is simply a temporary crest in that single universal ocean. The particles do not have individuality. What matters is the precise pattern of vibration, the specific arrangement of energy in the field. This is why all electrons are perfectly identical, no matter where or when you find them. Nature does not make them one by one, it makes them as synchronized waves of the same eternal song. The quantum field perspective also explains why the creation and annihilation of particles are so natural in high-energy physics. When energy is concentrated enough, it can excite the field strongly enough to produce new ripples, new particles. When those ripples cancel out, the energy returns to the field. Nothing is ever truly lost, it simply changes form. The universe, therefore, is not a collection of isolated objects bumping into each other in empty space. It is a continuous, dynamic tapestry of vibrations where every point is alive with possibility. Even in the darkest vacuum, every field hums faintly, carrying the echoes of everything that has ever existed and everything that ever could. The universe isn't made of things, it's made of patterns, waves and fields woven together into the song of existence itself. At first glance, empty space seems like the most boring thing imaginable, a void, a total absence of matter and energy. But in the quantum world, nothing is never truly nothing. Even the deepest vacuum, stripped of every last atom, every photon, and every trace of heat, still seethes with invisible intense activity. Space itself trembles with fluctuations as quantum fields constantly shift and flicker. It is a kind of cosmic background hum, so faint and so fast that it usually goes unnoticed, yet it is powerful enough to subtly shape the universe itself. This is the truth of the restless ground state. In classical physics, a vacuum is simply the simplest possible state, a region completely devoid of particles. But quantum field theory does not allow for perfect stillness. According to the fundamental uncertainty principle, you cannot know both the exact energy and the exact duration of a state at the same time. If a region of space were truly at zero energy, its lifetime would have to be infinite, and the universe does not seem to permit such absolute stillness in practice. Instead, the omnipresent fields in empty space constantly borrow and repay tiny amounts of energy, creating fleeting disturbances that appear as particle-antiparticle pairs. These pairs form spontaneously, live for unimaginably short times, and then instantly annihilate, restoring the energy they borrowed. These ghostly events are called vacuum fluctuations, and though they sound like pure science fiction, their effects are rigorously measurable. In fact, they are essential to the stability of the quantum world. Without these fluctuations, the electromagnetic field would fall silent, forces would behave very differently, and the entire structured flow of quantum processes would cease. The quantum vacuum isn't merely a stage on which physics happens. It is an active, vital participant in every process that occurs. When a particle and its antiparticle briefly pop into existence, they behave just like their long-lived counterparts, exerting tiny, measurable forces before disappearing again. One famous consequence of this is the Lamb shift, discovered in 1947 by physicist Willis Lamb. By measuring the energy levels of electrons in hydrogen with extreme precision, he found a small discrepancy that classical quantum mechanics couldn't explain. The missing ingredient turned out to be the restless vacuum itself. The fluctuating electromagnetic field slightly perturbs the orbiting electron, nudging its energy just enough to be detected. This subtle shift was one of the first, compelling pieces of direct evidence that empty space is, indeed, far from empty. Another striking and direct manifestation of the vacuum's energy is the Casimir effect, first predicted in 1948 by Dutch physicist Hendrik Casimir. Imagine two uncharged, perfectly conducting metal plates placed very close together in a vacuum, separated by just a few nanometers. According to quantum theory, the electromagnetic field inside and outside the plates can support certain modes of vibration, like the harmonics of a violin string. However, between the plates, only waves that fit exactly into the narrow gap are allowed. This physical restriction means there are slightly fewer vacuum fluctuations in the narrow gap than in the wide open space outside. This profound imbalance creates a tiny but persistent pressure, pushing the plates together as if an invisible hand were gently squeezing them. The force is incredibly small, but it has been measured many times in laboratories, providing a quiet, unmistakable reminder that the vacuum itself can exert a real, physical push. This same restlessness helps explain some of the most puzzling phenomena on the cosmic scale. The accelerated expansion of the universe, for example, is the leading cosmological mystery. The favored explanation involves vacuum energy, the cumulative effect of all those relentless quantum fluctuations adding up to a small but persistent outward pressure, often referred to as the cosmological constant. In theory, the total vacuum energy should be astronomically immense, far greater than anything we observe. But for reasons still not fully understood, this vast energy mostly cancels itself out, leaving behind only a faint residue that drives the ongoing slow acceleration of cosmic expansion. This staggering mismatch between the theoretical prediction and the observed tiny energy density is known as the cosmological constant problem, and it remains one of the biggest, most fundamental unsolved mysteries in physics, linking the subatomic world to the structure of the cosmos itself. Even the most extreme objects in the universe are not immune to the vacuum's mischief. In the 1970s, Stephen Hawking showed that quantum fluctuations near the event horizon of a black hole can create real particles. When a virtual particle-antiparticle pair appears right at the edge of the event horizon, one may fall into the black hole while the other escapes, carrying energy away. To an outside observer, it looks as though the black hole is slowly radiating heat, a process now called Hawking radiation. Over immense timescales, this radiation can cause a black hole to lose mass and eventually evaporate entirely. It is a breathtaking example of how the so-called vacuum can rewrite the fate of the universe's most extreme gravitational objects. What is perhaps most astonishing about all this is how precisely these phantom effects can be measured. The corrections caused by vacuum fluctuations have been verified in experiments that agree with theory to more than 1 part in a trillion. When physicists calculate the magnetic moment of the electron, the tiny magnetic signature of the particle, the contribution from the restless vacuum must be included to get the correct answer. Without it, the prediction would fail. That level of agreement is a triumph not just of experimental measurement, but of our understanding. It shows that even our emptiness obeys precise, elegant, and quantifiable rules. The vacuum's restlessness also carries a deep philosophical weight. It blurs the line between something and nothing, between existence and absence. When quantum fields fluctuate, they create a sea of potentiality from which reality continually emerges. Every photon of light, every atom of matter, every spark of energy was in some sense born from this churning, active background. The vacuum isn't a void. It is the foundation of reality, an invisible ocean whose endless waves build everything that floats above it. Nothingness, it turns out, is simply another form of something, one that quietly and consistently sustains the existence of everything else. At the heart of every atom, and embedded in the history of all light, lies one of the most essential and stabilizing discoveries in all of science. The simple, profound fact that energy comes in steps, not slopes. This principle is called quantization, and it dictates that electrons can't simply orbit a nucleus at any random distance or energy level. Instead, they can only occupy certain specific, allowed energy levels, like standing on definite rungs of a ladder. This single rule is what keeps the entire universe from falling apart. It is the reason atoms are stable, the reason light shines in distinct colors, and the reason chemistry possesses any structure at all. Without it, matter would blur into chaos, and everything we know would dissolve into an unbroken, continuous sea of energy. The idea of quantized energy was first conceived in the early 1900s when Max Planck was attempting to solve a baffling riddle about heat and light. Experiments showed that hot objects didn't radiate energy continuously. Instead, their colors shifted in predictable, abrupt ways as they warmed up. Classical physics was utterly incapable of explaining this. It predicted that hotter objects should glow with an impossible, infinite brightness in the ultraviolet part of the spectrum, the aforementioned ultraviolet catastrophe. Planck found that he could fix the problem, aligning theory with observation only by assuming that energy was released in discrete packets, or quanta, proportional to the frequency of light. A few years later, Albert Einstein applied Planck's bold idea to light itself. He showed that light sometimes behaved as if it were made of individual countable particles, photons, each carrying a precise quantum of energy. That leap of logic explained the photoelectric effect, where light knocks electrons free from metal surfaces. Only photons above a certain frequency had enough energy to deliver the singular necessary punch to do this, no matter how bright the light beam was. It was a clear, unmistakable sign that nature was not continuous but granular, built from tiny, countable units of energy. Nowhere is this more evident than inside the atom itself. When an electron orbits a nucleus, it is bound by the attraction between opposite charges. According to older classical physics, the electron should be able to orbit at any distance, radiating energy continuously as it spirals inward until it inevitably crashes into the nucleus. But that doesn't happen. Atoms are stable and electrons remain suspended in neat, well-defined orbits. Niels Bohr solved this critical puzzle in 1913 by formally proposing that electrons could only occupy certain allowed energy levels, specific rungs on the atomic staircase. To move between these rungs, they must absorb or emit a precise amount of energy in the form of a photon. That simple, quantized picture gave rise to one of the most beautiful and useful signatures in all of science, atomic spectra. When you heat a gas or shine light through it, the atoms absorb or emit light only at particular, distinct wavelengths. Viewed through a prism, these appear as bright or dark lines, like unique barcodes or fingerprints specific to each element. Hydrogen's lines form a simple, elegant pattern of reds and blues.
Helium's are more complex.
These spectral fingerprints allow astronomers to identify the chemical makeup of distant stars and galaxies, even millions of light-years away. Every point of light in the night sky carries a record of these quantum energy steps imprinted upon it. Quantization doesn't just determine the color of light. It fundamentally dictates the structure of matter itself. Each electron in an atom must find an available energy level, and no two can share the same one with the same spin thanks to the Pauli exclusion principle. This ordered stacking of electrons in quantized shells gives rise to the periodic table, where elements repeat in predictable patterns based on how easily their outermost electrons can jump between these energy levels. Chemistry, in all its diversity, from the stability of noble gases like neon, whose shells are full, to the high reactivity of elements like sodium, which have one easily detachable electron, is simply the elaborate choreography of electrons moving up and down the quantized energy staircase. Each of those jumps releases or absorbs photons with energies that correspond exactly to the gap between the specific levels. Small jumps produce low-energy light like infrared or red. Large jumps create high-energy light like ultraviolet or even X-rays. Even the familiar neon signs and fluorescent lamps rely on this principle. Electricity excites electrons to higher levels, and as they fall back, they emit light of characteristic colors. Every glowing city skyline is a silent, macroscopic testimony to these quantum steps. The concept of quantized energy extends beyond single atoms into the world of molecules and solids. In molecules, the same rules apply to vibrations and rotations. Bonds between atoms can stretch or twist only in discrete modes, each with its own quantized energy. In solids, electrons occupy bands of allowed energies separated by forbidden gaps. The size of these gaps determines whether a material is a conductor, an insulator, or a semiconductor. Without quantized bands, computers, LEDs, and nearly every modern technology would be impossible. The entire modern world of electronics, chemistry, and material science rests on the quiet, orderly discreteness that quantization imposes on energy. It might seem strange that nature would prefer steps to slopes, but quantization offers a crucial benefit: stability. If energy were continuous, even the smallest disturbance could drain or add energy endlessly, destabilizing every structure. Quantized systems, on the other hand, have well-defined ground states, the lowest possible energy they can possess. Once electrons settle there, they can't fall any further. The universe's preference for discrete levels acts as a safety net, preventing atomic collapse by setting hard floors and ceilings for energy exchange. At a deeper level, quantization reflects the wave nature of everything. Just as a guitar string can only vibrate in specific standing wave modes, electrons trapped around a nucleus can only form wave patterns that fit perfectly within the atomic boundary. These standing waves correspond to discrete energy levels. When an electron transitions between them, it's like the string jumping from one note to another. The music of the atom is a literal symphony of quantum harmonics. The discovery that energy comes in packets was one of the greatest intellectual revolutions in human history. It forced us to abandon the comforting smoothness of classical physics and embrace a world that changes in sudden, discrete leaps. Yet within those leaps lies order, precision, and beauty. Every atom's stability, every chemical bond, every flash of light is a tiny celebration of quantization, nature's quiet insistence that even energy, the most fluid thing imaginable, must still obey the rhythm of steps. It reminds us that the universe is both continuous and granular, a flowing sea built from indivisible ripples, and it is in those ripples, those tiny leaps between possibilities, that the difference between chaos and structure, darkness and light, truly begins. The story of quantum physics isn't just told through abstract equations and difficult theories. It is written, most vividly, in a series of groundbreaking experiments that didn't just confirm the mathematics, but fundamentally changed the way we perceive reality. Each discovery acted like a chip taken away from the comfortable assumptions of classical physics, replacing them with a truth that was far stranger, yet astonishingly accurate. From beams of light knocking electrons free to single particles, painting complex interference patterns, these iconic quantum experiments provided the unsettling, irrefutable evidence that the universe is far weirder than anyone expected. At the dawn of the 20th century, physicists thought they had a complete understanding of light. It was a wave, beautiful, continuous, and predictable. Then the photoelectric effect arrived like a crack in that certainty. This experiment involved shining light onto a metal surface, which caused the metal to immediately eject electrons as if the light were physically knocking them loose. Classical wave theory predicted that brighter light carrying more total energy, should always release more electrons regardless of its color or frequency. But that was not what experiments showed. Only light above a certain specific, Frequencies such as blue or ultraviolet could eject electrons. Increasing the brightness of a red beam, which is below that frequency threshold, did absolutely nothing. It didn't matter how intense a red beam was, it simply couldn't dislodge a single electron. Albert Einstein in 1905 made the daring suggestion that light's energy wasn't spread smoothly, but was carried in discrete, indivisible packets, photons. Each photon had an energy proportional to its frequency. Therefore, blue light carries more energy per photon than red light. The photoelectric effect proved that light could behave like a particle, not just a wave. For this profound insight, Einstein won the Nobel Prize, and the wave-particle duality of light became the first great, unsettling pillar of quantum theory. But nature wasn't finished turning our intuitions upside down. If light could act like a particle, could particles also act like waves? The answer came in 1927 when physicists Clinton Davison and Lester Germer were investigating how electrons scattered off a nickel crystal. They unexpectedly found a pattern that shouldn't exist: bright and dark fringes of intensity, exactly like the interference patterns created by light waves. Their discovery confirmed Louis de Broglie's bold prediction that matter has fundamental wave-like properties. Electrons weren't tiny, solid marbles. They were ripples in a quantum sea, capable of interfering and diffracting just like light. That revelation inspired one of the most haunting experiments in all of physics, the double-slit experiment performed with single particles. When light or electrons pass through two narrow slits, the hallmark of wave interference, a pattern of bright and dark bands, is created. But when scientists sent individual photons or electrons through the slits one at a time, the very same patterns slowly emerged. Each particle seemed to interfere with itself, as though it had gone through both slits simultaneously. Yet if detectors were placed to determine which slit the particle actually passed through, the interference vanished, replaced by two distinct
stripes, as if the particle had suddenly made up its mind.
The chilling conclusion was inescapable: observation changes outcome. Reality does not commit to one version of events until it is forced to. Until then, everything remains in superposition, a haze of possibilities waiting to become real. This experiment has been repeated with atoms, molecules, and even large organic compounds, and the result never fails to astonish, acting as a mirror reflecting the strange relationship between knowledge and existence itself. As physicists delved deeper, they stumbled upon something even more counterintuitive: entanglement. The idea that two particles could remain linked across vast distances, sharing properties in a way that defied all classical logic, was deeply unsettling. Einstein dismissed it as spooky action at a distance, convinced that hidden variables must exist to explain the correlations. This led to John Bell's work in the 1960s, where he formulated mathematical limits, Bell's inequalities, that any local hidden variable theory would have to obey. Over the next few decades, experimentalists, notably Alain Aspect, refined the technology to test these inequalities using entangled photons. The results were stunning. Quantum mechanics predicted correlations stronger than any local hidden variable model could allow, and that is exactly what was observed. The universe truly does exhibit non-local correlations, proving that reality at its deepest level is built not from isolated parts, but from instantaneous relationships that stretch across space. What began as a philosophical challenge became one of quantum mechanics' most profound and accurate tools. The experiments grew even subtler, probing the quantum world with almost unimaginable sensitivity. One of the most consequential effects is quantum tunneling, which allows particles to pass straight through energy barriers they classically should not be able to cross. The light of the sun, for example, owes its very existence to tunneling, which allows protons to slip through the repulsive electrical energy barrier to fuse, preventing stars from remaining dark and cold. Here on Earth, tunneling is the principle. behind the scanning tunneling microscope, STM, an instrument so sensitive it can image and manipulate individual atoms by measuring the tiny quantum current that tunnels across a microscopic gap between a metal tip and a surface. The STM is a direct, visible testament to the fact that the quantum world bends the rules of probability just enough to keep both creation and technology going. Even at the macroscopic level, quantum effects have been demonstrated in devices like SQUIDs, superconducting quantum interference devices. These devices, based on the Josephson effect, utilize loops of superconducting material to create a superposition of opposing currents. By measuring the interference between these quantum states, SQUIDs can detect changes in magnetic fields as small as a few trillionths of a Tesla, sensitive enough to pick up the magnetic activity of the human brain. They are living proof that the coherence and interference once thought to belong only to single atoms can, with enough isolation and care, be scaled up. Each of these experiments, from Einstein's photoelectric effect to modern SQUIDs, pushed the boundary of what physicists believed was possible. They taught us that light is both wave and particle, that matter shares the same dual nature, that observation shapes outcomes, and that even emptiness is alive with connection. The quantum world may be strange, but it is also astonishingly consistent, revealing the same truth again and again. Reality at its smallest scales is woven not from things, but from probabilities, patterns, and relationships. These experiments didn't just test equations, they forced humanity to rethink its understanding of the universe, proving time and again that the act of looking is profoundly a part of the story. Quantum mechanics may sound like something that only belongs in research labs or thought experiments, but it is the invisible, indispensable framework that quietly powers the modern world. Every screen you look at, every smartphone in your hand, and every computer chip that processes data is built upon the strange rules that govern atoms and waves. This is the ultimate realization of the quantum journey, the quiet quantum engine, running seamlessly beneath the surface of digital life. The most ubiquitous example is the transistor, the tiny switch that fundamentally changed human history. A single computer chip can contain billions of them, each one turning electrical currents on and off faster than any mechanical part ever could. Transistors work because of quantum mechanics. They are constructed using semiconductors, materials where electrons don't roam freely, as in a metal, nor are they strictly locked in place, as in an insulator. Instead, electrons occupy specific energy bands which are allowed by quantum rules. Between these bands is a forbidden region called the band gap, where electrons cannot exist. By carefully adding impurities, engineers can precisely tweak how easily electrons jump across that gap, creating materials that behave like one-way streets for current. The very logic gates inside your phone and computer are nothing more than quantum tunnels, carefully shaped by human design. The rules that make quantum mechanics seem weird, discrete energy levels, tunneling probability, are the same rules that make digital technology possible. Without them, there would be no laptops, no satellites, and no modern civilization built on information. From transistors, it is a short, quantum leap to the source of light itself. Quantum physics explains precisely how light and matter exchange energy, one photon at a time. This is the principle behind LEDs, or light-emitting diodes, which are so common we rarely pause to consider their profound quantum nature. In an LED, electrons are injected into a semiconductor where they fall from a higher energy band to a lower one, releasing the energy difference as a photon. The color of the light depends on the size of the band gap. A small gap gives red light, a larger gap produces blue. This process is elegantly efficient because every photon is born from a single, directed quantum jump, not from waste heat. The same idea powers lasers, perhaps the most famous quantum devices of all. A laser, which stands for light amplification by stimulated emission of radiation, relies on coaxing electrons into excited states and then encouraging them to fall back in unison. releasing identical synchronized photons. These photons then stimulate others to do the same, creating a cascade of perfectly synchronized light waves. The result is coherence, light that marches in lockstep, with every wave crest aligned with the next. Because of this precision, lasers can cut through steel, carry vast amounts of data through fiber optic cables, and perform delicate eye surgery. Every smooth, intense beam you see is a perfectly tuned quantum chorus, singing one note in unison. Solar cells are also built on this same principle, only in reverse. Instead of turning electrical energy into light, they turn light into electricity. When a photon strikes the surface of a solar panel, its energy can lift an electron across the semiconductor's band gap, creating a free charge that flows as current. This photovoltaic effect, a process Albert Einstein first explained in 1905, is the core of the world's most promising source of renewable energy. Depending entirely on the specific quantum jump between light and matter, if quantum physics governs how we make energy and light, it also governs how we measure time. The ticking of an ordinary clock depends on mechanical motion, but the ticking of an atomic clock depends on the oscillations of atoms themselves. Scientists learn to use microwave radiation to probe the transitions between the energy levels of cesium atoms, which occur with astonishing regularity, 992,631,770 cycles per second, to be exact. That number defines the second. Modern atomic clocks are so stable they lose or gain less than a second over the entire age of the universe. Global positioning systems, GPS, rely on them to synchronize satellites and calculate precise positions. A tiny timing error could throw off a location by several meters. Every minute, every time stamp, every digital heartbeat in our world is kept in tune by the quiet, quantum rhythm of electrons jumping between quantized energy states. Another remarkable application of quantum physics is found inside hospitals, the MRI scanner, magnetic resonance imaging. The MRI works by probing the quantum property of spin in the nuclei of hydrogen atoms in the body's water molecules. When placed in a strong magnetic field, these spins align like tiny compass needles. A precise radio pulse nudges them out of alignment, and as they relax back, they emit faint signals. By detecting and mapping these signals, the machine builds detailed images of the body's interior without a single incision. The clarity of those scans, down to millimeters, comes directly from the predictable quantum behavior of nuclear spins in magnetic fields. It's a way of listening to the body's atoms hum their quiet, characteristic tune. Each of these technologies illustrates the same profound truth. Quantum mechanics isn't confined to laboratories or thought experiments. It's woven into the very fabric of everyday life. The lights in your room, the internet carrying this very sentence, the navigation system guiding you home, all depend on electrons leaping between quantized levels and photons following the probabilistic rules first glimpsed more than a century ago. Even seemingly mundane materials owe their properties to quantum mechanics. The color of metals, the transparency of glass, the hardness of diamonds, all stem from the arrangement of electrons in quantized energy bands. Looking ahead, the boundary between quantum technology and everyday technology is fading fast. Quantum computers, quantum sensors, and quantum networks are the next evolution. But in truth, the quantum revolution has already happened. It began when engineers first learned to shape the energy bands of silicon and capture the light of a single photon. The world around you hums quietly with quantum precision.
Every glowing pixel, every electronic pulse, every perfectly timed signal is part of a vast, invisible orchestra.
Electrons, photons, and atoms performing their subtle symphony beneath the surface of ordinary life. And that brings us to the end of tonight's quiet journey through the quantum world, where certainty fades, probabilities hum, and even empty space is full of possibility. If you enjoyed drifting through these one-on-one quantum facts, it would really help the channel if you gave the video a like. It may seem small, but those likes tell the algorithm that this kind of calm, educational content is worth sharing, and it helps other curious minds find it too. If you're new here, please consider subscribing to The Whispering Scientist for more relaxing explorations of science, space, and everything in between. And for those already subscribed, thank you so much for being part of this growing peaceful community. Don't forget to tap the notification bell so you'll know when the next video is ready to drift off with. I'd also love to hear your thoughts and ideas. If there's a topic you'd like to see explored slowly and calmly in a future video, feel free to leave a suggestion in the comments. Until next time, may your thoughts settle gently, your curiosity stay bright, and your night be full of quiet wonder.